In this section, we begin our journey into frequency domain analysis of discrete signals passing through systems. Just like decoding how a music player reshapes sound, we will reveal the rules by which a system modifies digital signals. The knowledge framework for this section mainly includes the following aspects. 1. Frequency response of discrete time systems. 2. Steady-state response of e to the power of j omega k through an LTI system. 3. Response of an arbitrary signal through a system. 4. Response of a signal through a linear phase system. By studying these topics and mastering these principles, we will be able to design digital filters and optimize audio processing systems. Now let us start with the first stop, the frequency response of discrete time systems. Okay, looking at the definition of the frequency response of a discrete time system, we can see that its calculation method is the same as that for continuous time systems, and it likewise includes the magnitude response and the phase response. The discrete time frequency response is like the system's passport, recording two key pieces of information. The first is the magnitude response, i.e. the modulus of the frequency response, like the system's volume control for different frequencies. High-frequency attenuation reduces harsh noise. Low-frequency boost enhances the beat of music. The second is the phase response, i.e. the phase angle of the frequency response, like the system's delay timer for each frequency. Positive phase means the signal leads. Negative phase means the signal lags. At the same time, we can see a unique property of discrete time systems compared with continuous time systems: periodic repetition. Every 2 pi in digital frequency, the frequency response characteristics repeat. We only need to focus on the core band from -pi to pi, analogous to the human hearing range of 20 Hz to 20 kHz. Having understood the components of the frequency response of a discrete time system, we next study the special role of the complex exponential signal. This pure single frequency signal is the system's touchstone, just like using a pure color to test a display's color reproduction. When such a signal passes through the system, the output is still a signal of the same frequency. Its amplitude is scaled by the system's volume control and its phase is shifted by the system's delay timer. For this type of signal acting on a system, the resulting output is called the steady-state response. So, what are some application scenarios? One example is factory quality testing of headphones. A 1 kHz pure tone is fed into the headphones to measure their frequency response curve. From the output corresponding to this single frequency input, we can work backward to deduce the characteristics of an unknown system. The theoretical principles behind this process are exactly what we cover in this section, and they also lay the groundwork for analyzing arbitrary signals. Let us also consider a question. If we use the frequency of middle C on a piano, 261.6 Hz, to test the system, will the output pitch change? The answer is obvious. The output pitch will not change. This is because a single frequency signal acting on the system, like our complex exponential, only changes the phase of the system's output and does not generate extra frequency components. Building on the previous content, we now extend the complex exponential signal to arbitrary signals. Specifically, if the DTFT of the output signal exists, then according to the inverse discrete time Fourier transform formula, the first step is to decompose the signal, as in equation 1, breaking the input into a combination of complex exponential signals. The second step is system modification. According to the system's linear time invariant property, each frequency component can pass through the system independently, as in equation 2. The third step is to recombine the outputs to synthesize the final response signal, taking the discrete time Fourier transform of both sides of equation 2 yields equation 3, the spectrum of the zero-state response of the system to the excitation signal. equals the product of the spectrum of the excitation signal and the system's frequency response. This conversion of time domain convolution into frequency domain multiplication avoids complicated mathematical operations and directly shows how the system reshapes the spectrum. It is suitable for complex waveforms such as speech or biomedical signals. Next, let us look at the response of a signal through a linear phase system. As the formula shows, the relationship between a linear phase system and frequency is linear. A linear phase system is a time magician, whose core feature is that all frequency components experience the same time delay, so the signal waveform remains intact and undistorted. For the response of a linear phase system to an arbitrary input signal f of k, as in equation 1, we can see that the system's group delay is k0. The engineering value of a linear phase system includes, for medical equipment such as ECG testing, it can preserve the ECG waveform accurately. For audio processing, it avoids metallic distortion. For imaging systems, it can prevent edge blurring. What harm can a nonlinear phase system cause? For example, in a choir, if different voice parts have inconsistent delays, the singing will become chaotic. Here is a question for you to think about. Why must high-end recording studio equipment adopt linear phase design? In a recording studio, equipment such as microphone preamplifiers, equalizers, compressors, and reverberators may all involve signal processing. If the phase response of this equipment is not linear, what effect will it have on the audio signal? First, phase distortion will cause sounds of different frequencies to reach the listener's ears at different times. Although the human ear is not sensitive to absolute phase, it is very sensitive to changes in relative phase. Second, recording studios generally use multi-track recording. Phase differences between different tracks may add up, making the overall sound blurry and muddy, especially in the high-frequency range. Because high-frequency signals have shorter wavelengths, phase changes have a more significant effect on time delay. In short, the fundamental purpose of adopting linear phase design in high-end recording studio equipment is to maintain phase consistency of the signal, avoiding transient blurring, frequency cancellation, and stereo image confusion caused by differences in time delay, thereby achieving accurate sound reproduction. In this lesson, we studied the frequency response of discrete time systems. We learned that it includes magnitude and phase responses and is periodic. We mastered the steady-state response of complex exponential signals and its applications. We learned methods for analyzing the response to arbitrary signals. And we understood the waveform-preserving characteristics and engineering value of linear phase systems, as well as the fact that nonlinear phase can cause signal distortion. That concludes all the content of this lesson. See you next time.